Welcome in .Core. We've always been following every update on the Voyager missions here on this channel. But ever since the idea of a Voyager 3 was raised, one question keeps coming up. Is there a specific date when such a mission must launch? In other words, why did NASA send Voyager 1 and 2 in 1977? Why not earlier and why not later? In this video, we'll dig into that very question and uncover the reasons behind one of the most perfectly timed space missions in history. The Grand Tour opportunity, the late 1970s alignment, was more than a curiosity. It was a turning point in space exploration. Normally, visiting all 4 giant planets would have required separate missions, each demanding significant fuel and decades of planning. But in this rare configuration, a single probe could move from one planet to the next using their combined gravitational pull. Mission planners had identified the alignment as early as the 1960s. They envisioned a Grand Tour program that would send multiple spacecraft on extended journeys. Budget concerns forced NASA to scale down, but the core idea survived. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed on September 5th on a faster path that allowed it to overtake its twin within a few months. The missions were designed with different goals. Voyager 1 would focus on Jupiter, Saturn, and Titan before heading outward, while Voyager 2 would attempt the full sweep: Jupiter, Saturn, Uranus, and Neptune. The alignment dictated everything: the trajectories, the instruments, and the pacing of the encounters. At each flyby, the spacecraft would not only collect data, but also adjust its course toward the next target. This method transformed planetary exploration. Instead of consuming massive amounts of fuel, they rode the natural architecture of the solar system using gravity itself as their engine. By acting in that year, NASA ensured that discoveries about these distant worlds could be achieved in a single era rather than spread out across centuries. Without this launch window, much of what we know today about the outer planets might still be unknown. Transformative discoveries. The payoff from this carefully planned mission was immense. At Jupiter, they revealed details of the Great Red Spot, lightning storms, and intense radiation belts. Io stunned scientists with the first observed volcanic activity beyond Earth. Europa's cracked icy shell suggested a hidden ocean beneath, a possibility that remains central to the search for life. At Saturn, it exposed intricate ring systems, showing fine structures and unexpected features like transient spokes. Voyager 1's close pass by Titan confirmed that it had a thick nitrogen-rich atmosphere, thicker than Earth's, making it one of the most intriguing moons in the solar system. Voyager 2 pressed onto Uranus in 1986. It revealed a planet tilted on its side with a strange magnetic field, faint rings, and a collection of previously unknown moons. Though its atmosphere appeared bland, the discoveries about its orientation and magnetosphere raised new questions about planetary formation. In 1989, Voyager 2 reached Neptune, uncovering supersonic winds, the Great Dark Spot, and Triton's nitrogen geysers. Triton, with its retrograde orbit and active surface, hinted at a captured world still geologically alive. These encounters condensed centuries of planetary science into just over a decade. Each flyby provided a first close-up look at worlds that had only been dots of light through telescopes. The results reshaped scientific models from understanding ring dynamics to considering subsurface oceans as potential habitats. None of this would have been possible without the timing of 1977. The alignment made it possible to capture an entire family of planetary systems in a single extended mission, changing our view of the outer solar system forever. Into interstellar space. When the planetary flybys ended, they continued outward, extending their mission beyond its original scope. Voyager 1 traveled above the plane of the solar system, while Voyager 2 went below it, offering different vantage points. In 2012, Voyager 1 crossed the heliopause, where the solar wind yields to the interstellar medium. Voyager 2 followed in 2018, confirming the crossing from a different direction. These milestones made them the first human-made objects to enter interstellar space. Even now, both probes return valuable data. They measure cosmic rays, plasma density, and magnetic fields, helping researchers understand the heliosphere's protective boundary and the environment that surrounds our solar system. Though their power supplies are fading, engineers have managed resources to keep instruments running far longer than expected. Beyond science, they carry the golden record, a cultural time capsule with sounds, images, and greetings from Earth. It was meant as a gesture, a message to any intelligence that might encounter them in the distant future. While the scientific returns are measurable, the symbolic impact of the golden record is immeasurable. It marks them as more than machines. They are emissaries of human curiosity. At distances of more than 20 billion kilometers, with signals taking over 18 hours to reach Earth, they remind us how far foresight and planning can carry us. Their endurance underscores the value of launching when the conditions were right, ensuring discoveries and data long after the original mission ended. Outro: NASA's Voyager mission succeeded because they seized a rare planetary alignment in 1977, an opportunity that comes only once every 176 years. In one era, the spacecraft revealed volcanic moons, icy worlds, and the secrets of the outer planets. Now traveling through interstellar space, they remind us that exploration isn't just about technology, but about acting when the universe opens a door. Want more stories of cosmic opportunity? Subscribe and keep exploring with us. Thanks for watching Dark Core.